Yeah, today it's a great pleasure to have Eliot Quataert. Eliot is a professor of astrophysical sciences and Charles A. Young Professor of Astronomy at Princeton University. He's an astrophysics theorist who works on a wide range of problems, including stars and black holes, plasma astrophysics, and how galaxies form. He has received a number of national awards for his research, including the Warner Prize of the AAS, the Packard Fellowship, a Simons Investigator Award from the Simons Foundation, and elected membership in the American Academy of Arts and Sciences and the National Academy of Sciences. And he's also a highly regarded teacher and public lecturer. And today we have a Blackboard talk, the first one in astronomy, as someone was noting, about the origin of quasi-periodic eruptions.
Great, thanks. It's great to be back. So first, why Blackboard talk? Primarily because I feel like over the pandemic, everybody's forgotten how to do that. Doing everything on Zoom slides. So doing it on the Blackboard. I also think for certain topics, this is basically an ideas project where the paper consisted entirely of order of magnitude estimates. So that's particularly conducive to a Blackboard talk. And then the last is that it's actually way, way, way easier to prepare a Blackboard talk. You don't have to fuss over the slides and the pictures and whether everything was just so. You just have to jot out a few random things on the iPad. So that's another advantage. So this is work done with Wenbin Liu, who is now a faculty member at UC Berkeley, was a postdoc at Princeton for a year after being a postdoc at Caltech. And it's on phenomena that are called quasi-periodic eruptions, which is a newly discovered phenomena at the center of galaxies, and that, as I'll explain, is related in some ways to the tidal disruption of stars. It's the gentler cousin, a gentler way that stars can be destroyed by a black hole at the center of the galaxy than tidal disruption. So first, where actually having slides would be useful, but I'll sketch for you what the observations are. And I should say, this is a newly discovered phenomena, so there's like 4 examples of this that are known. It's a relatively new phenomena, but if you look at the centers of some galaxies, and please, I know there's a range of levels, so please interrupt if you have questions as I go. If you look at the centers of some galaxies, and the most interesting candidates, I think, were discovered by Zeta, which is the new all-sky X-ray survey, and so that opened up the discovery of this kind of rare phenomena. What you see is a source that looks like this. It's X-ray luminosity as a function of time. This time scale is like a few 10 hours. This time scale is like 5 to 10 times shorter. So half an hour to a few hours. The time averaged X-ray luminosities are something like 10 to the 42 ergs per second. This is maybe a factor of 10 to 100. So the amplitude of the X-ray flare is a factor of 10 to 100, although as I'll describe, that turns out to actually be a strong function of exactly what energy photons you look at. So this means that if one interprets this as some kind of accretion phenomena, that it's a time average accretion rate onto a central black hole of maybe 10⁻³ or 10⁻⁴ solar masses a year. And these are rare. So these are significantly rarer than the tidal disruption of stars at the centers of galaxies, which we've now detected hundreds of, and Zeta on its own is detected hundreds of. The rate at which these form is not very well known, in part because we don't know exactly how long these sources live in this state for. A few of them have been observed for something like 5 years. But if the lifetime is 100 or 1,000 years, which I'll argue is the case, then the formation rate of these objects to explain the number that have been seen and the volume that you or Zeta looked at is something like once every 10 million years in a galaxy. And so that's 100 times rarer than the tidal disruption of a star by a supermassive black hole.
Those peaks persist for 5 years?
Yeah.
Wow.
So yes and no. There's 4 systems. There's already a really rich phenomenology. In one case, the source disappeared for a while, but the flares stopped and then came back on. And so there's a lot of interesting phenomenology to try to explain. I'm largely not going to focus on that because I think we haven't had a good zeroth order picture. And so I'm going to focus on sort of the zeroth order picture of what can produce this kind of phenomenon. But there's a rich phenomenology.
Are these also from galactic centers?
These are from galactic centers, that's right. And they're from an interesting bit of the phenomenology is that they seem to be from relatively low mass galaxies. So implying relatively low mass supermassive black holes. So a million solar masses, maybe even a little bit less.
So what's the quasi? Is there a period derivative? Or
the quasi is that there are fluctuations in the period. In a couple of cases, it's actually the period between successive peaks differs by like 1% in a very regular way. In other cases, it just seems to be some jitter in the period. In one case that may be a related phenomena, which is an event discovered by Assassin, there is a period derivative measure. In the bulk of these cases, there's not a clear period derivative. I'll come back to that. Okay.
How many periods have we observed?
Yeah, so in a couple of cases, we've observed this for 5 years, so periods of hours. Well, sorry, it has been, we haven't observed it continuously during that time, but the evidence is that it was on for 5 years, so many cycles.
You said there are 4 such sources,
yes,
right? And they're observed at different times.
Yes.
Do they exhibit similar behavior when they observed, or there's
so there, you mean, do the 4 different ones have the same phenomenology?
so like you have one source and you observe different times, for example, the one you've mentioned.
So one source disappeared and then came back, the others didn't do that. So.
But like the behavior stays similar within the source, or
I would say from a theorist trying to develop a zeroth order model, yes, the behavior stays similar. There are lots of
but there's room for classes.
There's definitely already room for classes. That's right.
Out of 4 sources, already room for classes.
Yes. One and yes.
Exactly.
Reinforce.
As I said, I'm going to ignore that. Try to focus on a zeroth order picture. Okay. So when these were first discovered, the initial set of models actually focused on accretion disk phenomena. The idea being that there are, for instance, there are X-ray binaries in our galaxy which do some crazy things, not quite this crazy, but there's a famous system, GRS 1915, which is an X-ray binary near the Edmonton luminosity galaxy, whose X-ray light curve does absolutely astonishing things. If you haven't seen it, just Google the XTE X-ray light curves of GRS 1915. And so the interpretation of that strange behavior of that X-ray binary is that there are known instabilities of accretion disks where radiation pressure dominates over gas pressure. And so there have been models proposed of this phenomenon where this is driven entirely by intrinsic variability in the accretion disk. I think we can't rule that out because there's a lot we don't understand about accretion disks. when they're radiation pressure dominated. But it would be extremely strange if, 4 systems out of millions of systems that are radiating near it in the regime where radiation pressure dominates showed this phenomenon, and all of the other million minus 4 didn't. And so that, I think, is one argument against the accretionist phenomena. The other is that the systems in which these have been found, in particular the ones discovered by Rosita, aren't normal accretion disks. They don't have broadline regions. They don't look like normal spectroscopically classified AGN. They're in galaxies which would really not typically be classified as being active galactic. So it doesn't, again, look like it's a phenomena associated with normal accretion disk activity. So the models that I'm going to focus on are instead models in which this is driven by mass transfer in the star and the black hole. And this period, okay, of a few to 10 hours is identified with the star's orbital. So I first want to stress that this association is immediately extremely interesting. So just to remind you, in the center of our galaxy, those amazing movies by Reinhard Genzel and Andrea Ghez of stars orbiting the black hole. The most famous of those stars, SO2, has an orbital period of about 16 years. Okay. And so here we're talking about stars that have orbital periods of a few to 10 hours rather than 16. So these are stars much, much, much closer to the central black hole than the stars at the center of our galaxy.
How close can they get before their tidal disruption?
So that's the story is related. So these are stars that are in the process of being eaten by the black. So the semi-major axis is about 10 to the 13 centimeters. If the orbital period is 10 hours, and the mass of the black hole is 10 to the 6 solar masses. So again, this is comparable to the distance between the Earth and the Sun. So that's the scale of the orbit, which that follows basically just directly from associating the observed orbital period with that of a star, the observed period with that of an orbital period of a star. And this is about 100 gravitational radii, again, for a million solar masses. The star is very close to the central black.
But there are measurements of the black hole masses.
There are not any direct measurements of black holes measured. There are no stellar dynamical measurements. There's no broadline region.
So the estimate is just from the mean external velocity.
So no, the estimate of the black hole mass is from the fact that these are low mass galaxies. And the problem with that is that at low galaxy masses, there's much more dispersion in black hole galaxy correlations. And so the black hole masses could be 10 to the 5 solar masses, it could be 10 to the 6 solar masses. Okay. So I now want to distinguish between sort of two possible regimes in which, so the picture is we have a star with this orbital period, and going to be on a somewhat eccentric orbit, exactly how eccentric I'll get to in a second. So this is the semi-major axis of the orbit, the closest distance to the black hole, the pericenter distance, A times 1 minus E. And the model is going to be that is very similar to the radius, the tidal radius at which you start to strip mass off of this. And the tidal radius is just the stellar radius times the mass ratio to the 1/3. So you'll notice, right, if I take a black hole mass of 1,000,000 solar masses, stellar mass is about the mass of the sun, that's a factor of 1,000,000. Take that to the 1/3 power, that's about 100. Okay, so if I take the semi-major axis and divide it by 100, I get about the radius. So a star with about the radius of the sun on an orbit like this is going to be near its tidal radius where mass starts to get. So tidal disruption is the phenomena when a star comes in from large distances and it's on an orbit where its pericenter distance is significantly smaller than the tidal radius. And so in one passage, as the star goes by the black hole, it gets completely ripped apart, completely destroyed. You get this debris stream going off, produces all kinds of interesting electromagnetic observations. The case we're interested in here is different. The star, right, has to survive for a while because it's producing this phenomena over and over again. So the picture is actually that the star starts out outside the tidal disruption radius, but its orbit is decaying by gravitational wave radiation. And so it's getting closer and closer to the black hole. And at some point, it gradually approaches this radius, and then mass starts to get stripped off, and then you can initiate this phenomenon. So this is the star gets sent in impulsively on to its death, and this is the more gradual cousin.
Then after you brown down quite a bit, would you have a classic TDE of whatever's left over?
I don't think so for reasons that I'll get. Okay, so it turns out that in these models, explaining how you get a short duty cycle phenomena like this, so this is a large amplitude flare and then not much, most of the time it's not doing much, then another large amplitude flare. That's actually a quite interesting constraint on models of this phenomenon. And the reason for that, so the basic picture, right, is you're stripping mass periodically off of the star. That mass will start to build up in an accretion disk around the black hole. That accretion disk can do all kinds of interesting things like they usually do, including producing X-ray. The challenge is that the time scale for matter to accrete in an accretion disk, so if we're at some radius r, the time scale for stuff to accrete to smaller radii, if you're at radius r in the accretion disk, is generally much, much longer than the orbital period. It's longer by two factors. One is related to the viscosity, the momentum transport in the disk, and the other is related to the geometric thickness. But this accretion time scale is generally much longer than the local orbital period of the material. And that actually makes it hard for accretion in this kind of situation to produce a short duty cycle effect, right? You might, the initial thought might be, let me associate this spike with accretion of all the material that was ripped off the star each orbit. Okay, the problem is it takes the material many hundreds or thousands of orbital periods to actually accrete. So the only way you can do this, the only way this is possible, is if the eccentricity is actually extremely close to 1. So one model for this phenomenon would be that the viscous time at the pericenter distance of the star, the distance of the closest approach, is small compared to the orbital period. And the only way that's actually achievable is if the eccentricity is very, very close. So then the pericenter radius is much, much, much less than semi-major axis. So then this is true at pericenter. The viscous time at pericenter is long compared to the orbital period at pericenter. But that can still be small compared to the orbital period if the semi-major axis is much larger than the viscous.
Eliot, you said this evolved because of gravitational radiation.
Yes.
So you haven't said anything about the process by which, with the time it takes to radiate that.
That's right.
And this is happening
I'll come
with a very highly eccentric thing, and it just starts to get to that final radius at some point.
Yes.
And it doesn't work out with the gravitational.
If at this distance from the black hole, the gravitational wave in spiral time is less than the age of the star, so that's definitely the case. So the orbit can evolve on time scales that are significantly less than the age of the star. But I'll come back to that. That time scale is interesting. So this is actually very hard to satisfy. This would require, it can't be a main sequence star because any main sequence star whose pericenter distance is much less than 10 to 13 centimeters is already completely disrupted. So this would require the model to be a white dwarf. It would probably require an intermediate mass black hole, also rare and improbable. So I think this scenario is unlikely. There's other reasons for rate reasons that getting a star this close to the black hole with an eccentricity extremely close to 1, but not getting tightly disrupted in one passage is also extremely challenging.
Just entertaining that model for a minute.
Yep.
If you did get there, do you expect it to circularize on a time scale short compared to the lifetime of this?
So that's part of the problem. So if you started the star at a semi-major axis that was even just a few times larger than this, then it would have circularized by gravitational waves before reaching the semi-major axis. So that's part of a huge fine-tuning problem in maintaining that eccentricity.
And what happens when T accretion is the period? That's a sweet spot where everything is in limbo till gravitational waves kind of grind you in closer.
Sorry, when T accretion
is roughly the same as the period.
Yeah, so I'll argue that actually the natural hierarchy to consider is that the accretion time scale is long compared to the orbital period, which means that whatever these flares are, they can't be due to accretion. Because the picture then is every orbit, you're adding mass to the accretion disk, but it takes it a very long time to accrete. So all you're doing is building up a supply of mass. So this is the case that I'll focus on. So in this case, the eccentricity can be 1/2 or 2 or something like that. It doesn't have to be super close to 1. This can be a main sequence star because I no longer have this issue of having a pericenter distance, which is tiny compared to 13 centimeters. And in fact, I'll argue for reasons that I'll get to, that the stars of interest are less than about half the mass of the sun. Doesn't have to be an intermediate mass black hole, it can be a million solar mass black hole. But this has its own challenges. The accretion can't power the flare. And so we think what's going on instead is that what is actually powering this flare is the circularization. So every time at pericenter matter is stripped off of the star, that material that's stripped off of the star then orbits around, slams into the rest of the disk that is there, and gets incorporated into the disk. And that circularization process can power a short duty spectrum. So this is similar to what are called hotspots in X-ray binaries or accreting white dwarfs. The difference is normally those hotspots aren't particularly bright compared to the rest of the accretion process. But because the star is only located, 10 or 30 or 100 times outside the event horizon, the amount of energy in this circularization process is much higher than it is in normal accreting binaries. And so you can get a lot of luminosity out of this.
Doesn't the hotspot start to spread out?
It does. That's right.
What's the characteristic time for that?
So what happens is the material that's stripped from the star basically has to sweep up its own mass as it runs into surrounding disk material. And then over the time scale of sweeping up its own mass, the material will decelerate, lose its kinetic energy, turn into radiation, power flare. And that time scale, given the properties of the disk that we think will be formed, that time scale is actually short compared to the world. And so it decelerates and sort of becomes part of the disk on a time scale that's relatively short.
But these periodic pulses require the hotspot to maintain its integrity.
So probably the key time scale here actually ends up being the time scale for the radiation to diffuse out of the disk as the debris stream interacts with the disk and decelerates and mixes. The radiation then has to diffuse out. That's probably the rate limiting step that sets this duration. So the gas not maintaining its integrity is actually a good thing here because we want it to lose its energy by mixing with everything else. That's sort of how you tap into this energy of the debris stream to power the radiation.
Yeah, so Eliot, in tidal disruption events, people talk about the shock.
Yes.
There it is the intersection of the stream with itself, not with the disk. So it's a different story here.
I think it could. I think it could still be stream. I think that's an interesting. There's both stream and stream disk. The difference here is there's a disk that has much more mass than the stream because of this hierarchy of timescales. There's a disk present that has much more mass than the stream. So that's the more obvious thing for it to decelerate on, I think. Yep.
So doesn't the fact that you're sending this little potential of the star around the black hole to the disk also, like, do you drive spiral shock through the disk every periodic happens, or is the perturber too small?
I'll come back to that.
Okay,
so I think the more important thing is actually the effect of the disk on the star.
Oh, cool.
And I'll argue that that's actually what sets this MDOT. Is the disk is destroying the star, not that the star is affecting the disk. And the star doesn't affect the disk that much because the mass ratio is so small.
Okay.
Right? The mass ratio here is smaller than the Earth to the sun. And so it's really, if you think of the planetary analog, it's like a super low mass object, which doesn't really generate much in the way of spiral waves, doesn't open a gap in the disk, right? Okay, so the bigger effect it'll turn out is the disk. Okay. So accretion can't power the flare, I think it's circularization shocks. Another corollary is that there has to be a quiescent disk there, not just these flares, right? The accretion time is long, so there's a disk building up. And indeed, you do see emission between the flares. And in 2 of the 4 cases, last one QPEs, those 2 cases, it's actually quite interesting because if you look as luminosity as a function of photon energy, the flare looks like that. And the quiescent disk here looks like this. So it's faint at about a keV, but it actually dominates the bolometric luminosity. So again, 2 of the 4 cases, there's clear evidence that there is another component in the system which is not varying in time, which is actually dominating the time average luminosity. Which is, we think, this quiescent disk. And what's special about the flares is that they come from this relatively small area, the hot spot, as it mixes with the disk. And so that makes it hotter than the average disk emission. So it stands out as a bright flare at KV, but not in the bolometric luminosity sense.
Yep. So this average X-ray luminosity you put in at the start, that's just the flare, right?
No, this is, so I was quoting the time average. So that's averaging over time.
So that,
sorry, no, good. So you're correct. Here, when I quoted the time average, this is the time average of the flare.
yes. So what's the, you said these last for 1,000 or 10,000 years. I mean, what's the radiative efficiency?
The radiative efficiency of the flare is probably 1% or so, which is basically just 1 over this number. That's the energy available given the semi-major axis of given the scale of the orbit.
Okay, yeah.
So yeah, the radiative efficiency of the circularization is only a little bit less than that of a normal disk because the star is so close to the cloud.
A quick question. You always say that we're
Yep.
So there is luminosity dashed. It's without the flare, and then the second peak appears when there is a flare. Or
So this is there all the time,
uh-huh.
and then this is the thing that comes before. So gravitational waves are causing, so given the measured semi-major axis, the gravitational wave decay time scale of the star in its orbit depends primarily actually on the eccentricity. But in our case, the assumption that it's a main sequence star and the assumption that the pericenter distance is about the tidal radius fixes the eccentricity. Because I know the semi-major axis, I know the radius of the star I want. So I know the eccentricity, and that is about 0.5, 0.2, 0.5. It's a little different in some of the different systems that have slightly different periods. But given that eccentricity, the time scale for the star's orbit to decay is 10 to the 6 or 10 to the 6. So that's good. It's less than the lifetime of the system. So you can sort of bring the star in from further away. But the natural m dot that you would expect in this kind of problem is the stellar mass divided by the gravitational wave timescale. What is the timescale that gravitational waves are inevitably forcing the star deeper and deeper into the gravitational potential of the black hole and hence peeling mass off? And this m dot is much smaller than the actual time average m dot that we need to explain the observations. So that's another challenge that one is inevitably driven to by sort of the chain of reasoning that I've gone through.
Just a simple question about the light curve.
Yeah.
So it seems like, I mean, isn't the hot spot there all the time? And don't you see it for half the orbit? So what makes the spike so much narrower than that?
So first, it's 5 times narrower, so it's not that much narrower. So what makes the spikes narrower is that the matter is stripped only at a small range of azimuths in orbit right around Paris. Right, the vast majority of the orbit, the star doesn't have much mass stripped. Small fractions of it has. And this, the fact that this is shorter than this is part of the reason why the eccentricity can be 0.5 or 0.2, but it's not good to have it be 0. If I have a circular orbit, then I have no particular time that's special in terms of the stripping mass. So that's why it should be a finite eccentricity. Okay. So the resolution to this problem of the accretion rate, we think, is that this mass transfer is actually what's called unstable mass transfer. So when the star when a star loses mass, in this setup, the orbit actually doesn't change. The star loses mass and it loses orbital angular momentum and orbital energy. The mass gets stripped off the star, the orbital angular momentum is lost from the star, and it goes into the disk. So the star's orbit doesn't change. And then what's critical is how does the star respond to that mass loss? If the tidal radius goes up as the star loses mass, then you have a runaway. So that's the unstable case. If the tidal radius goes down, as the stellar mass goes down, then this is stable mass. So implicit in trying to make this association is that the mass transfer is stable, that you need gravitational waves, okay, to continuously force things together, to continuously strip mass. If the stellar radius goes up enough as the stellar mass goes down, then you have a runaway process and you don't need gravitation to drive continued mass. And it turns out that this is actually true if the stellar mass is less than half a square. So this time scale, 10 to 6, 10 to 7 years, okay, is an interesting time scale from the point of view of stars. So if you take a star like the sun and you take mass off of it extremely slowly, right now the sun is losing mass such that its mass will change after 10 to 14 years. That's an incredibly long time scale compared to all the other time scales that the star cares about. And so as you strip mass off the sun from its stellar wind, its radius can easily adjust to be that of a new main sequence star. This time scale is actually shorter than the time scale that it takes a star to come into thermal equilibrium, Kelvin-Helmholtz time. And in that limit, when you strip mass off a star initially on this time scale, you're actually stripping it off pretty quickly. And for low mass stars, they actually respond adiabatically to that mass being stripped off. And the adiabatic evolution of the radius of a low mass star is that its radius goes up like m to the minus 1/3. And so that's exactly in this unstable. And you can check this, you can take MESA stellar evolution models and you can strip mass off at some rate and ask how does the radius change as a function of mass? And for low mass stars only, so for low mass stars only, when you initially start stripping mass off on a time scale of 10 to 6 or 10 to 7 years, the radius of the star responds by actually expanding. So that generates this runaway unstable mass transfer. And so what that means is gravitational waves initiate the mass transfer, but once the mass transfer gets going, it's a runaway. And this is very similar to what leads in certain situations to stellar mergers in binary systems in stellar evolution. So we sort of have a similar situation here where the star is spiraling in, it's losing mass, and that sort of triggers something that is analogous to a merger. Now it's a merger between a half a solar mass star and a million solar mass black hole. So it's clear who wins that. Okay. Any questions about that?
And it goes the star and survive for even in the 3 years with 10 to the 42 Earths per second right next to it.
Right.
That set up for changes structure.
So we think so the irradiation of the surface by the X-rays is definitely an interesting bit of physics that changes the surface layers of the star a lot. We think the dominant thing that actually affects the structure of the star is that it's going to pass through the disk that it is creating. So mass getting stripped off the star starts to build up a disk, and now the star in its orbit is going to run through that disk. And we think this actually regulates the amount of mass that's stripped off the star. That this dynamical interaction is more important than the radiative interaction. So the picture is, right, here's the black hole. As time goes on, there's some disk that's been created. That disk starts to spread out in radius, and then the star, as it's orbiting around, during the course of its orbit, depending on the exact eccentricity and inclination, about inclination, the star will slam into the disk during some of its. And the interesting, the sort of amazing fact, which I realized going through this, so if you take an accretion disk that has an accretion rate of 10⁻³ solar masses a year, and you're at a radius which is like 30 to 100 RG, and the black hole mass is 10 to 6 solar masses. Standard disk models would predict that the density in the disk is about 10⁻8 grams per cubic centimeter, and that the ram pressure that the star feels as it moves through the disk, so that's the density of the disk times the velocity of the star in its orbit. Okay, the star is moving at 1/10 of the speed of light, right? Radius of 100 RG or so, velocity of the star is 1/10 of the speed of light. So this is the pressure produced by the shock as the star moves through the disk. This is about 10 to the 12 ergs per cubic centimeter. So just to give you something to compare this to, is the 10th of the speed of light also the relative velocity of the star? The 10th of the speed of light is also roughly the relative velocity of the star, because the star is on an orbit with an eccentricity of 1/3 or 1/2. The gas disk settles down to become on quasi-circular orbits, so the relative velocity between the star and the disk will be comparable to the velocity of light. That wouldn't be true if it was a circular. If the star was on a circular orbit, the relative velocity would be quite a bit less. But as long as the eccentricity is, 1/3 or something, that is a significant fraction. So the average pressure in a star is just Gm²/r⁴. This is about 3 × 10⁻⁵ ergs per cubic centimeter for a 1/2 a solar mass star. The other pressure you might wonder about is the pressure of the surface layers of the star. So the pressure in the photosphere, the surface layers of the star, is just gravitational acceleration divided by the opacity of the surface layers of the star. So this turns out for stars of interest to be about 10 to the 5. So the star is moving through a disk that generates a shock. The pressure associated with that shock is 7 orders of magnitude larger than the natural surface pressure of the star. And it's actually not that much smaller, it's a bit less. It's not that much smaller than the interior pressure. So as the star goes through pericenter, you drive a very strong shock into this disk-star interaction, drives a very strong shock into the star. It also drives a shock into the disk, of course, both of those. But the shock into the star comes out to be the more important.
When this thing is mostly stripped, don't you end up with something like a miniature white dwarf? And
yeah.
Does that change the story?
Well, I haven't yet stripped that much mass, so I'm not going to. But when you get to the very end, you might end up with a helium white dwarf or something at the center. I mean, it's all happening in the end in 100 or 1,000 years. So the core doesn't have time to really become as dense as a white dwarf. So I don't think the story is actually going to change when we get to the end. But I'll admit to not having like fully thought through what happens to the very last bits of the core. I think that's an interesting question.
What's the interaction between the star and the cluster that is from play in your role?
That gets the star down to this crazy orbit in the first place.
Because you need the binary. But
yeah.
Like so then you have a very elongated star. That's weird.
That's right. So the model, which I was going to come to at the end, is that this is produced similar to how we think the stars orbit the galactic center of groups, the S stars, which it is that it was initially a binary system at large radii. It comes in, the binary gets disrupted, one of the stars stays behind, one goes off as a high velocity star. The one that stays behind starts to spiral in by gravitational waves and ends up in the orbit on Earth. And the rates for that actually work out to be not crazy.
So because you already brought up again S stars, so we don't believe that S2 is the closest star.
No.
It's the one we see, right?
Yes.
So is it really that rare to get a star with a similar property so close to the black hole that it's like 1 in 10 million, you said?
Something like that. That's
so
right.
it's like statistically you'll get.
I think that getting a star on these orbits is not so easy. You have a somewhat higher rate of stars that end up on perfectly circular orbits, because if you start out at large radii, gravitational waves are much more efficient at damping eccentricity than some of your axis, so they'll drive you towards a very circular orbit. So that getting things on mildly eccentric orbits is a somewhat lower rate than getting perfectly circular orbits. The perfectly circular version of this is sort of interesting. Exactly what that will do is it won't produce something with flares like this. It'll be less easy to pick out observationally. But I do think the rates are pretty.
But that also gives you constraint on the properties of typical star clustering.
Galactic nuclei. Yeah, that's. And these estimates of rates are based on sort of standard assumptions about star clusters. So, okay, so that.
Just prior to starting to strip, would you start having astroseismic activity in the star?
Yes. Tides. The tides in the star are really interesting and might, might change the story a bit. I think what they'll probably do is they'll initiate mass transfer sooner than you thought by puffing. Tides will deposit enough energy into the star to puff it up. And that will sort of get the runaway process happening sooner than you think, which actually is a helpful thing from a rates point of view. It means more stars before the orbits have become perfectly circular might be susceptible to this phenomenon. But that's a hard, that the tides in this regime are of very large amplitude and very nonlinear. So that's a hard problem. But that's, I think that is probably important to that initial phase. So it turns out that if you take a star and you ask, if you drive a shock to a certain pressure, how much mass is affected? The mass that's shocked, this just follows actually from hydrostatic equilibrium. The mass that's shocked divided by the mass of the star is just the pressure associated with the shock that's driving the shock, divided by the average pressure. And this is independent of the outer structure of the star, because it does just follow from hydrostatic equilibrium. And so that means that every time the star slams into the disk, you completely change the outer 10⁻³ or 10⁻⁴ structure of the star by mass. And so we think a not crazy, we did more detailed calculations that I won't go into, but a not crazy first estimate of how much mass sort of gets puffed out by this star-disk interaction is that every orbital period, you shock this outer layer, it expands out, and then it gets tidally stripped by the tidal gravity of the black hole because you're near Paris. And so the time average m dot is, sorry, this P is orbital period. These P's are the pressure associated with the star. So this is happening every orbital period. So the time averaged m dot is something like this, actually a little bit less, because only some of the mass expands out to large enough radii that it gets stripped by the tidal gravity of the black hole, but let's not worry about that. So then the other interesting thing is that the pressure that the star feels depends on the m dot in the accretion disk. That sets the density and hence the pressure in the accretion disk. And so in principle, you can reach an equilibrium where the amount of mass in the disk is, and hence the pressure in the disk, is exactly that needed to supply the m dot. And if you do standard assumptions of accretion disks, radiation pressure dominated, etc., you find that this gives you the ram pressure at which that ram pressure can strip the needed m dot is an m dot of about, and it depends weakly on things in the problem, black hole mass, orbital period of the star, pericenter distance of the star, etc. But it's of order the answer.
It seems to me that the answer should be very different depending on whether the star is moving in the plane of the disk,
yes,
versus just cutting through the disk.
Yes.
So this estimate comes from what? Which assumption is this?
So this estimate comes primarily from the plane one, right? So I think the way to say this, so meaning what Ramesh is saying, right, is if this is the disk you get on and the star's orbit is something like that, that's a very different situation from the face-on view I drew before, where the star is within the same plane as the disk. So would most of them be out of the plane? No, because this disk is formed from the star. So its initial orbital plane is the initial orbital plane of the gas is the orbital plane of the star. The challenge then is, does lens-tearing precession force alignment of the inner part of the disk, or more precisely, does it force alignment of the outer part of the disk, which is the part that the stars actually interact with? That's a big open question, which is interesting. So the big difference, and this gets back to the question about the hotspot, is there's one way of thinking about how much mass the star is going to interact with as it plows through the disk is that the column density of material it sees, if it's coming vertically through the disk, is rho h, while if it's in the plane, it's rho r. So there definitely are, in this estimate, there are h over r's to various powers that show up depending on which situation. And that can change this number by factors of 3 or 4, probably not by a lot more than that. So I think we were happy that this is in the ballpark, but you're absolutely right about it. And so this issue of lens-tearing precession is an interesting outstanding.
Is there so if you looked at the width of these pulses or the changing over time of the distance of the time between pulses, or the total luminosity, are there tests that could check the model that the sequence of steps?
Yeah, so one prediction here is we're associating the mass transfer, which sets the luminosity of the system, with the properties of the disk, the density of the disk. This also produces a drag force on the star. So there's actually a prediction that the orbital period should be decaying because of its interaction with the disk, and that rate of decay should actually be a function of m dot, right? Because the density of the disk sets how much mass is stripped, and it also sets the drag force on the disk. So this, for most of these systems, this predicted period change is pretty small, so it's going to be hard to observe. There is a system that is, I think, actually related to this. It has a period, instead of in hours, it has a period of 115 days. This is the system Assassin 14KO. It's called a partial tidal disruption event. It's really the same basic thing. It's just 115 days, not 2 hours. So it's classified slightly different name. It is a quasi-periodic eruption, right? It has periodic eruptions, different time scale. In this system, P dot has been measured, and the discovery papers say we don't know what produces this, can't be gravitational waves, way too fast to be gravitational waves. If you just take all of this theory, in this case, the predicted P dot actually agrees with the observations. And the difference is this orbital period is much longer, so the drag force is able to change the orbital period more effectively. Right? The orbital energy is much less here because you have a large movement.
So there should be a longer wavelength signature, right? That makes sense, possibly. When
there should be, what do you mean a longer wavelength signature?
Right. Something in the, when you finished pulling out all the material from the star, and then you have just the almost.
Yeah.
You built up the disk now that is almost comparable to the original mass of the star.
Yep. So there's definitely a prediction here that, right, at the end of this process, when the star is mostly gone, you should have this unusual, very compact accretion disk, which should still live for several of its viscous times. And so some fraction of galactic nuclei should have these very unusual central sources. That's right. And so those would potentially show up as being objects that, because it lives for about, so the lifetime, I think, is set by this interaction. So this is a lifetime of 100 to 1,000 years, which is long enough that you can have a little bit of a narrow line region. So you might have some unusual sources that have a narrow line region, don't have a broad line region, that have weird, optical infrared spectra because the disk is very small. So most of the optical infrared emitting region isn't there. It's normally large radii. So that's correct. And so it's really a needle in a haystack. This is a very small fraction of galaxies that should have this, but that's an interesting thing to try to look at. Okay, so I'm basically out of time, but I think I hit most of the main points I wanted to hit. So what are some of the big, I talked about some of the things that I think work in the model, some of the things that are uncertain actually have already been brought up. I would say the biggest, most interesting theoretical uncertainties are the role of tidal heating, which can change the outer layers of the structure of the star prior to the onset of mass transfer. And then understanding better whether or not the disk that the star is interacting with actually is forced to be aligned with the spin of the black hole. So that's this Bardeen-Pedersen alignment question. And one might have very different kinds of, there might be interesting differences in the observational manifestation if the star is going through the disk like this, or if the star and the disk may stay in the same plane, at least in the outer part. So I think those are parts that need to be understood a little bit. But this is ours, again, as I started with, I wanted to convey to you a zeroth order understanding of what is going on. This is our zeroth order understanding. And the other thing I think that's quite interesting about these phenomena is it really does suggest that there's a continuum of phenomena between tidal disruptions, which is when you get sent in on an orbit where the pericenter distance is small compared to the tidal radius, you're destroyed in one go. Partial tidal disruptions, which are periodic phenomena but happening on this longish time scale. And then these quasi-periodic eruptions, again, periodic phenomena happening in the relative. And then for me, at least, the last thing that got me really excited about thinking about this is that this kind of phenomena, a star orbiting at 30 or 100 Schwarzschild radii around a black hole, is sort of the holy grail for Lisa. What Lisa wants to see, though, is not a half a solar mass star orbiting at 30 or 100 Schwarzschild radii. It wants to see a white dwarf or a neutron star or a black hole orbiting at 30 to 100 Schwarzschild radii, because then that star will be basically a test mass and will provide a beautiful probe of the space-time of the black hole. These are these extreme mass ratio inspirals, MREs, that are one of the most interesting targets. And this is really the stellar version of that. How the star got there, how it interacts with the disk, etc. This is our observational window well before Lisa launches into this kind of phenomenon. We're not going to see electromagnetically a neutron star spiraling into a million solar mass black hole. It's not going to produce any light. It'll just be a gravitational wave source, but these are our electromagnetic window, and they're very similar. I think that's, for me, part of what makes this particular. I'll end there. Thanks.
I think the rate is a little puzzling to me still, right? Because you can expect to have more than one star doing this thing, contributing to the disk in the inner regions, right?
Not at a given time. Not at a given time. Okay. And the argument, I mean, the argument roughly for the rate. So is the rate of Q. So TDEs form, we think, when some star far away from the black hole undergoes stochastic two-body relax, stochastic interaction with other stars and gets kicked onto a very low angular orbit. We think that these form when the same thing happens, but you send in a binary star. So first hit on the rate is the binary fraction. And then the second hit on the rate is that most of the binaries that go in, so there's some semi-major axis of the binary. So what happens then, the binary goes in, the binary gets tidally disrupted, one star gets flung out of the system, one gets left on a highly eccentric orbit. Most binaries that get disrupted leave stars on such a long semi-major axis that they either don't have any gravitational wave effects on the orbits, or they become fully circular by the time they actually undergo rotational orbit. So the only ones that have a finite eccentricity are the ones actually where the super tight binaries, the ones that are hard to disrupt. So when the binary separation is just a few times the stellar radius, then the binary is disrupted at a small semi-major axis, and so that's much more likely to produce this kind of phenomenon.
It's another multiplicator. Yeah, I
small a.
So incorrectly thought that all you needed was the ratio of orbits, fraction of orbits.
Yeah, so it's this.
Suppression.
This is basically 2 factors of the 10th, roughly, right? So that's how we think is basically what is said.
So in the case where this disk is misaligned with respect to the stellar orbit, do you expect a dimmer pulse train of doublets or what?
Yeah, so that, okay, so now we can talk about there's actually some observations which really suggest the misaligned case. So there's two systems, which are not the same as the two systems which are the disk.
This is the other class.
I think one of them is, but it's not
One
exclusively the same. So if you measure the time between flares just as a function of time, so just keep a running count. Every alternate flare has a slightly different duration, and it's by like 3%. And the simplest explanation, I think, is that you have two encounters between the star and the disk. And if the star is eccentric, and we're not viewing the system exactly face on, there'll be a light travel time difference between those two. And that's, if the eccentricity is 0.1 or so, that light travel time distance can actually give you this alternating time ride. So the picture then would be, and pericenter, right, in the inclined case, generically pericenter is not at either of these. So the picture then would be each star-disk interaction strips a mass off the star. That mass follows around, slams into the disk here, produces a flare. Then the star hits the disk again, another one goes around, slams into the disk. So you, in that case, it would actually be two flares per orbit, not just one. And this is so regular that I have not been able to come up with any other explanation. I mean, maybe there is, but it really seems suggestive of the case that's misaligned. I still think I should say, so you might ask, if it's misaligned like this, do I need the disk to have anything to do with the star? Maybe there's just a normal AGN there, pre-existing disk, and I have some stars coming in doing interesting things. I think that of course must happen, but I think that is much lower on rate. And the reason is that the probability of an AGN being there is less than one, some disk that has a significant density, m-dots 10⁻³ solar mass a year, high Ram pressure to affect the star. That's like a less than 1% probability. The probability of getting a star on one of these orbits is a very low thing. And so the probability of the star interacting with the pre-existing disk, I think, is much less than the probability of the star interacting with its own disk and lens tearing precession being in the limit where it belongs. So that's my argument that it's still the same basic story, but I think it's mostly a rate. And it's also
likely to see broad lines.
Yeah, then there's no broadline region.
We have a couple of questions online, actually. The first one I'll read. Is there a chance that the orbital precession of the star induced by the star-disk interaction might be observable?
So there are three orbital precessions in the problem, all of which are potentially observable. There's lens tearing precession, there's the Schwarzschild precession of the orientation of the ellipse, and then there's precession induced by changes in angular momentum due to drag. The general relativistic precessions are actually not small, right? At a semi-major axis, so at a semi-major axis of 100 Schwarzschild radii, the change in the orientation of the ellipse every orbit is roughly 1 over the semi-major axis. So it only takes something like 1,000 orbits for the star to completely precess around. And that should produce arrival time changes that evolve secularly in the arrival of the flares. And so that is a potentially observable thing, if you can time these well enough, right? If they were pulsars, you could totally do this. They're not such good clocks. It's not clear to me that it's going to be doable, but that's the kind of thing. I think the dominant signal actually is the relativistic precession, not the precession induced by the star.
Yeah, and the second question line, sorry, there is Anita, you want to ask yourself?
Oh, yes, thanks. Thanks for a very interesting talk, Eliot. So I'm interested in the dynamics of interactions between the star and the disk, because in the past we were considering these interactions and calculating the amount of the matter which was taken out of the disk because of the wake which is generated by the shock. And I was wondering if that effect is also possible in your
So great question. So you could ask the question, who has the bigger dynamical effect on who? Is it the star on the disk or the disk on the star? And it turns out to be the disk on the star. So I think each slamming of the star through the disk, you strip more mass off of the star, then you sort of drag disk mass out with the star. So I think the dominant effect here actually is the effect on the star, not the effect on the disk in terms of how much mass is sort of sprayed out to subsequently slam into other mass and produce the flares. I think it really is the effect. So both are definitely present, but I think the dominant one is the change in the structure of the star by hitting the disk.
Yeah, thank you. I'll send you the reference because we were saying something different in the sense that it was the effect was generating the broad line region, so the interactions were happening farther out, and the
farther out. The unusual thing here in part is that close in the star is moving so fast that makes this ram pressure that the star feels even larger. And so this is different. It's in a different regime of star disk interaction than a lot of what is relevant at larger radiation.
Interesting. Thank you.
Can we connect to the mass of the star and the need for instability? So if these shocks are what's driving the pumping up and the heating, does it really need to be a low mass star in the first place?
So I think if I ignore tides, and I think it's.
Well, you want to get it started somehow.
I want to get it started.
Yeah.
So the problem is in a solar mass star, the mass transfer is initially stable, and I'm losing mass initially at 10⁻⁶ or 10⁻⁷ solar masses a year. And I think probably that just forms a Sagittarius star M87 like puffy geometrically thick flow in which the star and the disk are just completely dynamically decoupled. And so then it becomes just the gravitational wave driven process. With tides, though, I think it's totally possible that I can do this with any star, because tidal heating might puff up the solar mass star in a way that's similar to what unstable mass transfer is doing. So I think with tides, there's definitely the possibility of this happening to a wider range of stars. And that's just super interesting. It's a very interesting problem, but having worked on tides for many, many, many years, that's a hard problem.
So, Eliot, you said that the precession can happen on hundreds of orbits, right? So you got one of these guys that was observed over a period of 5 years. So over 5 years, the orbit in particular could have precessed like crazy. It could be completely different after 5 years.
Yeah.
So you mentioned that, timing details can change. I was thinking even things like Doppler boost can change because you may be intersecting in a different part of the orbit.
Yes.
So what is actually known about this guy who was observed 5 years ago?
So you mean, for instance, how different are the flare, typical photon energy, typical luminosity? That's a good. I don't remember. I mean, there's one case where it disappeared for a while and then came back. So, one speculation is associating that with lens tearing precession, where maybe things are either more or less efficient if you're closer to the planar or out. But I think questions about just secular evolution and the observed properties and whether or not, I don't remember the observations well enough
Because if it was identical,
Yeah,
it would be worrying.
yes,
It should have
Yeah.
changed.
yes, there should be some now, the Doppler shift, these are sort of percent level effects.
No.
No, sorry,
No.
10% level
Yeah.
effects, 10% level effects.
There are not that many photons here.
They're not that,
Yeah,
and the luminosity, the flares are not the same luminosity every time. The photon energy part, actually, I don't know. That's an interest. Whether it would be interesting just to bin, one could certainly do something like what is the average luminosity at the beginning of this 5-year period, what's the average luminosity later? That would be interesting. I don't know if anybody's looked at that. So the person who's done a lot of the observational work on this is Ricardo Arcodia, who is actually coming to MIT as a Hubble Fellow starting in January from Max Planck at MPE. So you should definitely have, he's a good local-ish resource about all of the observations.
All right. Okay, last question.
I just have a question if there's any the resonant effects in the star.
So I think between the star and the disk, that's an interesting question. So one of the resonant effects that people talk about a lot for stars and disks interacting is that the star can excite waves in the disk. That's what happens in protoplanetary disks. That actually doesn't happen here because the star is moving supersonically relative to the disk. And so the interaction is very different. So the resonant interactions I've thought the most about are tides, which are basically resonances between the star and the orbit. So none immediately come to mind for the star and the disk, but that's just an off the cuff.
Okay, let's thank our speaker again.
Great. This is the way to do it.
Yes. It's fun.